Here's something most people get completely wrong about quantum cryptography. They think the security comes from the quantum physics itself, from Heisenberg's uncertainty principle or the no-cloning theorem. And sure, those are important. But here's the truth that nobody talks about. Even after Alice sends her photons and Bob measures them, the key they share is absolutely useless. It's filled with errors, it's noisy, it's partially known to Eve, and if they tried to use it right now, their entire communication would be compromised within seconds. So how do Alice and Bob take this broken, error-filled mess and turn it into something that even an adversary with unlimited computational power cannot break? That's what we're diving into today. And I'm warning you right now, this gets deep. We're talking about the actual mathematics, the real protocols, the stuff that textbooks skim over because it's too technical. But here's the thing. If you understand this, you understand how quantum key distribution actually works in the real world. Now, before we get into the error correction algorithm itself, we need to understand something fundamental that most explanations completely miss. And this is critical because without this piece, nothing else makes sense. Why do errors even exist in the first place? If Alice is sending quantum states and Bob is measuring them, and they're both using the same basis after sifting, shouldn't their bits match perfectly? Shouldn't the protocol just work? The answer is no. And the reason why reveals something profound about the gap between theoretical quantum mechanics and real-world quantum systems. Let's start with the most obvious source. The quantum channel itself is not perfect. When Alice sends a photon through an optical fiber, that fiber is not some magical lossless medium. It's a physical object made of glass, and that glass has impurities, microscopic bends, temperature fluctuations, and stress points. Every single one of these imperfections can scatter the photon, rotate its polarization slightly, or introduce phase noise that corrupts the quantum state. And here's what's fascinating. Even if the fiber were perfect, you still have coupling losses. The photon has to enter the fiber from Alice's source, travel through potentially kilometers of material, and then exit into Bob's detector module. At each of those interfaces, there's a probability that the photon gets absorbed, reflected, or sent in the wrong direction. These aren't eavesdropping events. These are just the brutal realities of trying to send single photons through real-world hardware. But it gets worse. Bob's detectors are not ideal quantum measurement devices. In theory, a detector should click with perfect reliability whenever a photon arrives, and it should never click when no photon arrives. In practice, avalanche photodiodes and superconducting nanowire detectors have dark count rates, meaning they sometimes fire randomly even when no photon is present. They also have finite detection efficiency, meaning sometimes a photon arrives and the detector just doesn't see it. And they have timing jitter, meaning the exact moment when a detection event is registered can vary slightly from the actual photon arrival time. All of these imperfections combine to create a situation where even after Alice and Bob perform basis sifting and keep only the cases where they used matching bases, their bit values still disagree in a small but significant percentage of positions. This disagreement rate is called the quantum bit error rate, or QBER, and in a typical deployed system, it might be anywhere from 1% to 5%. That means if Alice and Bob sifted a key of 10,000 bits, somewhere between 100 and 500 of those bits are just wrong. Bob thinks he has a 0, but Alice actually sent a 1, or vice versa. Now here's where it gets really interesting. These errors aren't just annoying, they're actually useful. Because if Eve is attacking the system, she almost always introduces additional errors. If she tries an intercept-resend attack, she forces the QBER up to 25%. If she's doing something more sophisticated, like a detector blinding attack or a photon number splitting attack, she might keep the QBER lower, but it still increases beyond what the natural channel noise would produce. So by measuring the error rate, Alice and Bob can actually detect whether Eve is present. But here's the catch. And this is the part that makes error correction so tricky. Alice and Bob need to correct these errors without revealing their actual bit values to anyone listening on the classical channel. Because here's the thing that's easy to forget. BB84 uses two channels: the quantum channel, where the photons travel, and the classical channel, where Alice and Bob communicate publicly to perform basis announcements, error correction, and privacy amplification. That classical channel is not encrypted. Anyone can listen to it. Eve is definitely listening to it. So every single message Alice and Bob send during error correction is public information that Eve hears. If Alice were to just say, "Hey Bob, bit number 47 should be a 1. Well, congratulations. Eve now knows bit 47 too. The entire point of quantum cryptography just collapsed. So the error correction protocol has to be clever. It has to give Alice and Bob enough information to find and fix their errors, but it can't reveal the actual bit values in the process. And that's exactly what the parity-based binary search protocol accomplishes. Let me walk you through how this actually works, step by step, with real mathematics. And I'm going to go slower than most explanations, because this is where people get lost. First, Alice and Bob take their sifted key and divide it into blocks. Let's say they split their 10,000-bit key into blocks of 1,000 bits each. The block size matters, and we'll come back to why. But for now, just understand that instead of checking the entire key at once, they're going to check each block separately. For each block, Alice and Bob compute something called the parity. The parity is just a single bit that summarizes the entire block. It tells you whether the number of ones in the block is even or odd. That's it. If there are an even number of ones, the parity is 0. If there are an odd number of ones, the parity is 1. This seems almost stupidly simple, but it's actually incredibly powerful. Let me show you the math. If Alice has a block of bits represented as a 1, a 2, a 3, all the way up to an, where n is the block size, then her parity is computed as parity equals a 1 XOR, a 2 XOR, a 3 XOR, all the way through XOR an. That XOR operator, exclusive OR, is the key to everything. Let me remind you how XOR works, because this is fundamental. 0 XOR 0 equals 0. 0 XOR 1 equals 1. 1 XOR 0 equals 1. 1 XOR 1 equals 0. In other words, XOR outputs 1 if and only if its two inputs are different. And here's the magic property. If you XOR together any even number of ones, you get 0. If you XOR together any odd number of ones, you get 1. So when Alice computes her parity, she's effectively counting how many 1 bits are in her block. But instead of giving Eve a number, she's only revealing whether that count is even or odd. That's way less information than the actual bit values. Bob does the exact same computation on his version of the same block. He takes B1 XOR, B2 XOR, B3, and so on. Now, Alice and Bob publicly compare their parity values. This is the first public message in the error correction protocol. Alice says, "My parity for block 1 is 0, and Bob says, "My parity for block 1 is 1. Here's what just happened. If their parities match, that means Alice and Bob have the same number of ones in that block, which means either the block is completely error-free, or there's an even number of errors that happen to cancel each other out in the parity calculation. The probability of the second case is extremely low in a real system, so matching parities almost always means the block is clean. They can move on to the next block, no further communication needed. But if their parities disagree, that immediately tells them something definitive. There is at least one error somewhere in this block. They don't know which bit is wrong. They don't know how many bits are wrong, but they know for certain that this block contains at least one mismatch. And now they need to narrow down where that error is hiding. This is where the binary search begins, and this is the part that's actually beautiful if you understand what's happening. Alice and Bob split the block in half. Let's say the block has 1,000 bits. They cut it into a left half with bits 1 through 500 and a right half with bits 500, 1 through 1,000. Now they repeat the exact same parity check, but only on the left half. Alice computes the parity of her left 500 bits. Bob computes the parity of his left 500 bits. They compare. If the left half parities match, that tells them the left half is clean. The error is not hiding in the first 500 bits. It must be in the right half. So they ignore the left half completely and focus entirely on the right half. If the left half parities disagree, that tells them the opposite. The error is definitely in the left half. So they ignore the right half and focus on the left half. Either way, they've just cut their search space in half with a single parity check. And here's the key insight that makes this algorithm so efficient. They repeat this process recursively. Let's say the error was in the right half. Now they split that right half into 2 quarters. They compute parities on each quarter. Whichever quarter shows a parity mismatch, that's where the error is. They ignore the clean quarter and split the bad quarter in half again. They keep going, half, quarter, eighth, 16th, and so on, until the search space shrinks down to a single bit. That bit is the error. Bob flips it, and the block is corrected. Let me show you the mathematics of how many parity checks this actually requires. If you have a block of size n, and there's one error in that block, the binary search takes log₂ of n steps to find it. For a block of 1,000 bits, log₂ of 1,000 is about 10 parity checks. That's it. Compare that to a naive approach, where you check every bit one by one. That would take 1,000 checks in the worst case. Binary search gives you a 1,000-bit block corrected with only 10 public messages. That's logarithmic efficiency. And it's the reason why error correction in BB84 is actually practical. But here's something critical that most people don't realize, and this is where the security analysis gets subtle. Every single parity check leaks information to Eve, not about individual bit values, but about relationships between bits. When Alice and Bob announce that the parity of bits 1 through 500 is 0, Eve learns that those 500 bits sum to an even number. When they announce that the parity of bits 251 through 500 is 1, Eve learns that those 250 bits sum to an odd number. Each parity message is a linear equation over the key bits, and Eve is collecting all of these equations. If Eve collects enough linearly independent parity equations, she could theoretically solve for some of the bit values directly, just from the error correction messages alone. This is why the amount of information leaked during error correction has to be carefully tracked and accounted for in the privacy amplification step. We'll come back to this because it's absolutely crucial to understanding why privacy amplification works the way it does. Let me walk you through a concrete example so you can see exactly how this plays out in practice. Let's say Alice and Bob have just finished sifting, and they're now looking at a 7-bit block. Alice's block is 1011000. Bob's block is 1011100. They don't know yet that they disagree in the 5th position. Bob thinks he has a 1 where Alice has a 0. Let's watch how the protocol finds this error. First, both of them compute the parity of the full block. Alice takes 1 XOR 0, XOR 1, XOR 1, XOR 0, XOR 0, XOR 0. Let's compute this step by step. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 0 is 1. 1 XOR 0 is 1. Alice's parity is 1. Bob does the same calculation with his bits. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 0 is 0. Bob's parity is 0. Alice and Bob compare. Their parities don't match. 1 versus 0. This immediately tells them the block contains an error. Now they split the block. The left half is bits 1 through 3. The right half is bits 4 through 7. Alice computes the parity of her left half. 1 XOR 0 XOR 1 equals 1 XOR 0 equals 1. Then 1 XOR 1 equals 0. Alice's left half parity is 0. Bob does the same. His left half is also 1 minus 0 minus 1. 1 XOR 0 XOR 1 equals 0. Bob's left half parity is 0. The left half parities match. This means the left half is clean. The error is not in bits 1, 2, or 3. It's definitely in the right half. So they focus on bits 4 through 7. Alice's right half is 1, 0, 0, 0. Bob's right half is 1, 1, 0, 0. They split this right half again. Bits 4 and 5 form one sub-half. Bits 6 and 7 form the other sub-half. Alice computes the parity of bits 4 and 5. 1 XOR 0 equals 1. Bob computes the parity of his bits, 4 and 5. 1 XOR 1 equals 0. Mismatch. The error is in bits 4 or 5. They check bits 6 and 7 just to confirm. Alice has 0 XOR 0 equals 0. Bob has 0 XOR 0 equals 0. Match. Bits 6 and 7 are clean. Now they know for certain the error is in position 4 or 5. They split again. Bit 4 by itself. Bit 5 by itself. They don't even need to compute a parity for a single bit. The bit itself is its own parity. Alice announces bit 4 is 1. Bob announces bit 4 is 1. They match. So the error is definitely in bit 5. Alice has 0 in position 5. Bob has 1. Since Alice is the reference in the protocol, Bob knows he's wrong. He flips his bit, 5, from 1 to 0, and now their blocks match perfectly. The error is corrected. And here's what's remarkable about this entire exchange. Eve heard every single parity message. She knows the full block parity disagreed. She knows the left half parity matched. She knows the right half parity disagreed. She knows bits 4 and 5 disagreed, while bits 6 and 7 matched. She heard that bit 4 was a 1 from both sides. But does Eve know what bit 5 is? No. She knows Bob flipped it, so she knows Bob originally had the wrong value and Alice had the right value. But she doesn't know whether Alice's correct value was a 0 or a 1. The protocol never revealed that. Alice and Bob only revealed relationships and parities, not the actual bit values. That's the genius of this approach. Error correction happens publicly, but the secrecy of the key is preserved. Now, there's a hidden complexity here that we need to address because it affects the security analysis. What if a block has more than one error? This is actually pretty rare in a real system with a low cuber, but it can happen. If there are 2 errors in a block, the parity check might actually show a match because 2 bit flips can cancel each other out in the XOR sum. If bit 10 is wrong and bit 20 is wrong, and both were supposed to be 0, but Bob measured 1, then Bob has 2 extra 1s in his block. 2 1s XOR together give 0, so the parity doesn't change. The block looks clean even though it has errors. Here's how real systems handle this. They use multiple passes. After the first pass of error correction, Alice and Bob randomly permute their bits and run the error correction again on the permuted blocks. If there were hidden errors that canceled out in the first pass, they're very unlikely to cancel out again after permutation because now they're in different positions relative to the block boundaries. After 2 or 3 passes with different random permutations, the probability of uncorrected errors remaining is essentially negligible. This is why practical BB84 implementations don't just run error correction once. They iterate until they're confident the keys match. But here's the critical question we've been building toward. Even after error correction is complete, even after Alice and Bob have verified that their keys match perfectly through multiple passes of parity checks and confirmations, is the key secure? Can they start using it to encrypt messages? The answer is absolutely not. And understanding why is the key to understanding privacy amplification. Because even though Alice and Bob now have matching keys, Eve still knows something about those keys. She gained information during the quantum transmission phase. If she performed any kind of attack, photon number splitting, detector manipulation, whatever, she obtained partial knowledge of the key bits. And she definitely heard all of the error correction messages, which gave her additional linear constraints on the bit values. Let me make this concrete with a simplified example. Suppose the sifted key was 10,000 bits long and the cuber was 5%. That means Eve's interaction with the quantum channel gave her some information. How much? Well, in an intercept-resend attack, a 5% cuber would mean Eve attacked a small fraction of the pulses and introduced errors on those. But the real answer depends on what attack Eve performed. The point is, Eve knows something. Then, during error correction, Alice and Bob exchanged maybe 100 parity messages to fix all the errors. Each of those parity messages is a linear equation that Eve heard. If she's clever, she can use those equations to narrow down the possible values of some key bits. She doesn't know the whole key, but she might know 50 bits out of 10,000 with certainty and have probabilistic information about hundreds more. Privacy amplification is the step that takes this partially compromised key and distills it into a shorter key that Eve has essentially zero information about. And here's the counterintuitive part. They accomplish this by throwing away bits. They take their 10,000-bit key and compress it down to maybe 7,000 bits. And somehow, that compression destroys Eve's knowledge while preserving Alice and Bob's shared secret. How is that even possible? How does making the key shorter make it more secure? This is where we need to understand the information theoretic argument behind privacy amplification, and this is honestly one of the most elegant ideas in all of cryptography. The core concept is this. Eve has partial knowledge about a long key. Some bits she knows. Some bits she has probabilistic information about. Some bits she knows nothing about. If Alice and Bob could identify which specific bits Eve knows and just delete those bits, they'd be done. But they can't do that because they don't know what Eve knows. So instead, they use a different strategy. They apply a universal hash function to their entire key. This hash function takes the full key as input and outputs a shorter key. The crucial property of a universal hash function is that it mixes all the input bits together in a highly nonlinear way. Every output bit depends on essentially all of the input bits. You can't reverse the hash. You can't figure out the input from the output. And here's the key property. If Eve's knowledge about the input key is limited, then her knowledge about the output key becomes exponentially smaller. Let me explain this with an analogy. Imagine Alice and Bob have a bag with 1,000 marbles, and each marble is either red or blue corresponding to a 0 or 1 bit. Eve has peeked into the bag and seen 50 of the marbles. She knows those 50 colors with certainty. The other 950 marbles, she's never seen. Now Alice and Bob pour all 1,000 marbles into a blender, mix them up thoroughly, and randomly pull out 700 marbles to form a new bag. What does Eve know about this new bag? Well, she knows something. She knows that 50 of the original marbles she saw are somewhere in that mixture. But here's the thing. Those 50 marbles are now completely mixed with 950 marbles she's never seen. And the new bag only contains 700 marbles total. The probability that any specific marble she saw is in the new bag is 70%. But the probability that she can predict the exact color sequence of all 700 marbles is essentially 0. The mixing and compression have destroyed her advantage. That's what privacy amplification does, mathematically. The hash function plays the role of the blender, mixing all the bits together. The compression plays the role of taking a subset, ensuring that Eve's known bits are diluted by the unknown bits. Let me show you the actual mathematics of how this works, because the security proof is based on something called the leftover hash lemma, and it's surprisingly beautiful. First, we need to quantify exactly how much Eve knows about the raw key. We use a measure called the min-entropy, which captures Eve's best-case probability of guessing the key in a single try. If the raw key has n bits and Eve has obtained r bits of information about it through eavesdropping and error correction, then the min-entropy is roughly n minus r. This represents how many bits of genuine unpredictability remain from Eve's perspective. Now, Alice and Bob want to compress this n-bit key down to a shorter m-bit key such that Eve's information becomes negligible. The leftover hash lemma tells us exactly how short we need to make the output. If we choose m to be less than the min-entropy minus 2 times log base 2 of 1 over epsilon, where epsilon is our security parameter, Then, after applying a universal hash function, Eve's ability to distinguish the compressed key from a truly random m-bit string is bounded by epsilon. Let me unpack what that means in plain language. The security parameter epsilon represents how close to perfect randomness we want to get. If epsilon equals 2 to the negative 40, that means the probability that Eve can tell the difference between our compressed key and a truly random key is less than 1 in a trillion. That's information theoretic security. Even with unlimited computational power, Eve cannot break it with probability better than 1 in a trillion. The price we pay for this security is that the output key is shorter than the input key. We have to compress by roughly the amount of information Eve gained, plus a safety margin that depends on how strong we want the security guarantee to be. This is why high QBER is so devastating. If Eve forced the QBER up to 10%, she gained a lot of information about the key, which means privacy amplification has to compress very aggressively, and the final key becomes very short. At a QBER of about 11%, the compression becomes so extreme that the final key length goes to 0, meaning no secure key can be extracted at all. That's the fundamental security threshold of BB84. Let me walk through a concrete calculation so you can see how this works numerically. Suppose Alice and Bob finished error correction with a raw key of 10,000 bits. They estimate that Eve gained about 1,000 bits of information from the quantum channel based on the observed QBER. During error correction, they exchanged parity information equivalent to about 500 bits. So the total information leakage is 1,000 plus 500 equals 1,500 bits. The min-entropy is 10,000 minus 1,500 equals 8,500 bits. Now, they want a security level of epsilon equals 2 to the negative 40. Plugging into the formula, the final key length must be at most 8,500 minus 2 times log base 2 of 1 over epsilon. Log base 2 of 2 to the 40th is 40, so the final key length must be at most 8,500 minus 2 times 40 equals 8,500 minus 80 equals 8,420. They can safely extract an 8,420-bit key with security parameter epsilon equals 2 to the negative 40. Notice what happened. They started with 10,000 bits after error correction. They compressed to 8,420 bitses. They threw away 1,580 bitses. That compression destroyed Eve's 1,500 bits of information, plus a little extra for the security margin. The output key is provably secure, meaning Eve's expected information about it is bounded by the security parameter, which is astronomically small. Now, how do they actually perform this hash compression in practice? The most common approach in real QKD systems is to use a construction called a Toeplitz matrix hash. This is a specific type of universal hash function that's efficient to compute and has well understood security properties. Here's how it works. Alice and Bob publicly agree on a random binary matrix with dimensions m by n, where n is the raw key length and m is the desired final key length. This matrix is public. Eve knows it too. The hash function is simply matrix multiplication. Alice takes her n-bit key, treats it as a column vector, and multiplies it by the m by n Toeplitz matrix. The output is an m-bit vector, and that's her final key. Bob does the same multiplication with his key, and because their keys matched after error correction, their final keys also match. The Toeplitz matrix structure ensures that this multiplication can be done efficiently using fast Fourier transforms, so even for keys with millions of bits, the computation is feasible. But here's what's crucial. Even though Eve knows the Toeplitz matrix, she cannot reverse the multiplication. Matrix multiplication is not invertible when you're going from a large space to a small space. There are many possible input keys that produce the same output key under the hash. And because Eve doesn't have full information about the input key, her partial knowledge gets scrambled and diluted by the mixing operation. The leftover hash lemma guarantees that her uncertainty about the output is exponentially large. Let me address a subtle point that trips people up. You might be thinking, wait, if privacy amplification is so powerful, why don't Alice and Bob just compress the key even more? Why not go from 10,000 bits down to 1,000 bits instead of 8,420? Wouldn't that be even more secure? The answer is no, because there's a fundamental trade-off between security and key rate. The leftover hash lemma sets a lower bound on how much you can compress based on the min-entropy. If you compress too much, you're throwing away genuine randomness, not just Eve's information. The output key becomes shorter than the min-entropy, and at that point, the security proof breaks down. Eve's information is no longer negligible. She might actually have a significant chance of guessing the key. So the optimal strategy is to compress exactly to the min-entropy minus the security margin. That maximizes the length of your final secure key while maintaining the desired security level. Going shorter gains you nothing. Going longer leaves you vulnerable. This is why the min-entropy calculation is so important. It determines the fundamental limit on how much secure key you can extract from your raw quantum measurements. There's another practical consideration that affects real systems. The min-entropy calculation requires Alice and Bob to estimate how much information Eve gained, but they don't know what attack Eve performed. They only observe the cuber. So, how do they estimate her information? The standard approach is to assume the worst-case attack consistent with the observed cuber. For a given error rate, there's a maximum amount of information Eve could have obtained, and that maximum is achieved by what's called an optimal eavesdropping strategy. Alice and Bob conservatively estimate Eve's information as if she performed this optimal attack. This is actually one of the beautiful aspects of BB84's security proof. You don't need to know what Eve did. You only need to know the cuber. From that single number, you can bound Eve's information, compute the min-entropy, and determine how much privacy amplification is needed. The security holds against any attack, including attacks that haven't been discovered yet, as long as the fundamental laws of quantum mechanics hold. Now let me show you why privacy amplification fails if the min-entropy estimate is wrong. This is absolutely critical for understanding real-world security. Suppose Alice and Bob measured a cuber of 3%, and they calculated based on that number that Eve gained 500 bits of information. They run privacy amplification assuming this estimate, compressing their 10,000-bit key down to 9,500 bits. But here's the problem. What if Eve actually performed a more sophisticated attack that didn't increase the cuber as much, but still gave her 1,000 bits of information? Now Alice and Bob think their 9,500-bit final key is secure, but Eve actually has 1,000 bits of information about the raw key that was compressed into that final key. The privacy amplification wasn't aggressive enough. It didn't compress away all of Eve's knowledge. The final key is partially compromised, and Alice and Bob have no idea. This is exactly what happens in attacks like detector blinding or time shift attacks. Eve manipulates the hardware in a way that gives her information without increasing the cuber proportionally. The min-entropy estimate becomes wrong, and privacy amplification fails. This is why countermeasures against hardware attacks are so important. You can have perfect privacy amplification mathematics, but if your estimate of Eve's information is wrong, the final key is not secure. Security in quantum key distribution is a complete package. You need quantum physics. You need error correction. You need privacy amplification. And you need to close all the hardware loopholes that allow Eve to gain hidden information. Let me also address one more common misconception. Some people think privacy amplification is just classical post-processing, and therefore it's not really part of quantum cryptography. They think the quantum part ends when Bob measures the photons, and everything after that is just ordinary information theory. This view misses the point entirely. Privacy amplification is what converts quantum mechanics into cryptographic security. Yes, privacy amplification uses classical hash functions, but the reason it works is fundamentally quantum. Eve's limited information about the raw key comes from the no-cloning theorem and the measurement disturbance principle. If you could clone arbitrary quantum states or measure them without disturbance, Eve could gain complete information without increasing the cuber, and privacy amplification would be useless. So the security of privacy amplification rests entirely on quantum foundations. The classical post-processing is just the mathematical tool that extracts the security guarantee from the quantum physics. Here's something that's really important to understand about the relationship between error correction and privacy amplification. They're not independent steps. The amount of privacy amplification you need directly depends on how much information you leaked during error correction. Remember, every parity message is a linear equation over your key bits. The more parity messages you send, the more information Eve gains. So there's actually a trade-off. If you use larger block sizes for error correction, you send fewer parity messages, which means less leakage. But larger blocks also mean that if there are multiple errors in a block, they might not be caught in a single pass. So you need more passes, which means more messages. If you use smaller blocks, you catch errors more reliably with fewer passes, but you send more messages overall because you have more blocks to check. Optimizing this trade-off is a real engineering problem in deployed QKD systems. Typically, systems choose block sizes on the order of several hundred to a few thousand bits, and they run 2 to 4 passes of error correction with random permutations between passes. The total information leakage is then tracked across all passes, and that total gets factored into the min-entropy calculation for privacy amplification. This is why you can't just think of error correction as separate from privacy amplification. They're tightly coupled in the security analysis. Let me show you one more really important concept that ties everything together: the secret key rate. This is the quantity that tells you how many secure bits per quantum signal you can ultimately extract from a QKD session. And it depends on all the factors we've been discussing: the sifting efficiency, the QBER, the error correction leakage, and the privacy amplification compression. The formula for secret key rate is approximately R equals 1/2 times the sifting efficiency times 1 minus the Shannon entropy of the QBER minus the information leaked during error correction, all measured in bits per signal. Let's break this down term by term. The 1/2 comes from the fact that Alice and Bob randomly choose bases, so on average only half the signals survive basis sifting. The sifting efficiency accounts for losses and missed detections in the channel. The Shannon entropy term represents the fundamental information theoretic cost of correcting the errors, even with optimal error correction codes. And the leaked information term accounts for the actual protocol overhead in the error correction process. Let's plug in some realistic numbers. Suppose the sifting efficiency is 50%, meaning half the photons make it through the channel and get detected. The QBER is 3%. The Shannon entropy of 0.03 is about 0.2 bits. The leaked information from error correction is about 0.1 bits per signal. The secret key rate is approximately 1/2 times 0.5 times 1 minus 0.2 minus 0.1 equals 1/2 times 0.5 times 0.7 equals 0.175. That's 0.175 secure bits per signal sent. If Alice is sending signals at 1 gigahertz, that's 1 billion signals per second, giving you 175 megabits per second of secure key. But that's in the best case. In practice, you also have finite size effects, statistical fluctuations, and additional safety margins, which reduce the rate further. But the point is, this formula tells you the fundamental limits on how much secret key you can extract from a quantum channel with given noise characteristics. And here's what's important. As the QBER increases, the secret key rate decreases. At low QBER, you get a high rate. At high QBER, the rate drops. And at a QBER of about 11%, the rate hits 0. Beyond that point, no secret key can be extracted, no matter how much privacy amplification you do. This 11% threshold is not arbitrary. It's a fundamental consequence of the information theoretic security requirements and the structure of BB84. Now let me tie this all back to why error correction and privacy amplification are both necessary and why neither one alone is sufficient. Error correction ensures that Alice and Bob's keys match. Without it, they'd have different keys, and any attempt to use those keys for encryption would produce garbage. So error correction is necessary just for functionality. But error correction doesn't remove Eve's information. In fact, it leaks additional information to Eve through the public parity messages. Privacy amplification does remove Eve's information. It compresses the key in a way that destroys her partial knowledge. But privacy amplification requires that Alice and Bob already have matching keys to start with. You can't compress two different keys and hope they'll match after compression. So privacy amplification requires error correction to run first. Together, error, correction, and privacy amplification form the complete post-processing pipeline that converts noisy quantum measurements into a secure, matching cryptographic key. And here's the final piece that makes BB84 genuinely secure. After privacy amplification, Alice and Bob can verify that they have matching keys by publicly comparing a short hash of their final keys. If the hashes match, they know with high probability that their keys are identical. If the hashes don't match, something went wrong. Either the error correction missed some errors, or Eve is actively interfering, and they abort. This final verification step catches any residual problems before the key gets used. So the complete BB84 protocol is not just send photons and measure them. It's send photons, measure them, perform basis sifting, perform multiple passes of error correction with parity checks, compute the min-entropy based on observed Kuber and error correction leakage, apply privacy amplification using a universal hash function, and verify the final keys match. Every single one of these steps is mathematically necessary for security. Let me give you one final perspective on why this matters so much. Classical key distribution, like Diffie-Hellman or RSA key exchange, relies on computational assumptions. You assume that factoring large numbers is hard, or that discrete logarithms are hard. If someone builds a quantum computer or discovers a fast classical algorithm for these problems, all of that security evaporates instantly. BB84, with proper error correction and privacy amplification, doesn't rely on computational assumptions. It relies on the laws of physics. As long as quantum mechanics is correct, and as long as you properly estimate Eve's information and apply the right amount of privacy amplification, the final key is secure against any adversary, even one with unlimited computational power. That's information theoretic security, and it's the entire reason quantum key distribution matters. But it only works if the post-processing is done correctly. If you skip error correction, your keys don't match. If you skip privacy amplification, Eve knows part of your key. If you underestimate Eve's information, privacy amplification compresses too little and Eve retains knowledge. If you overestimate Eve's information, privacy amplification compresses too much and your key rate becomes impractically low. Getting all of these steps right is what separates theoretical quantum cryptography from deployed working quantum key distribution systems. And here's the thing that should blow your mind a little bit. The mathematics of error correction and privacy amplification was worked out in the 1990s and early 2000s, decades after the original BB84 protocol was proposed. Early versions of BB84 didn't have rigorous privacy amplification. They used ad hoc methods that turned out to be insecure in certain attack scenarios. It took years of research to develop the full information theoretic framework we've been discussing, to prove the leftover hash lemma, to understand min-entropy and its role in security, and to figure out how to properly account for error correction leakage. This is still an active area of research. People are working on better error correction codes that leak less information, more efficient privacy amplification schemes, tighter security proofs that allow shorter keys for a given security level, and finite size analysis that accounts for the fact that real systems exchange a finite number of signals rather than the infinite number assumed in asymptotic security proofs. Every improvement in these areas translates directly into higher key rates and more practical QKD systems. So when you see a commercial QKD system advertising that it can generate secure keys over 100 kilometers at megabit per second rates, all of that performance comes from decades of work optimizing, error correction, and privacy amplification. The quantum physics is important, obviously, but the post-processing is just as important. You can't have one without the other. Let me leave you with this final thought. The beauty of BB84 is that it proves something that sounds impossible. Two parties who have never met who are connected by a noisy, lossy channel that's completely controlled by an adversary, can still establish a shared secret key that the adversary knows essentially nothing about, using only the laws of quantum mechanics and publicly observable classical communication. That's the promise of quantum cryptography. But that promise only becomes reality through the mathematics of error correction and privacy amplification. Without those steps, BB84 is just a physics experiment. With those steps, it's a revolution in secure communication. And that's why understanding this mathematics deeply is not just an academic exercise. It's the foundation of the future of cryptography.